Good morning, student. Today I am taking next class for gases and gases mixture. In this topic, we will cover idle gas law, Charles law, Boyle's law, and in gaseous mixtures we cover Dalton law, Amagat's law, and relationship between partial pressure, mole fraction and component mole fraction of component to total pressure. Then we calculate average molecular weight of gaseous mixture. From this average molecular weight, we will continue to density of the gaseous mixture. And in gas and liquid mixture, we will go through Rawls law and Henry law. Uh, we will focus more on calculation part, and you have already gone through this one, so you can take help of plus 2 test books also. This is calculation part, and I am making this video for you to learn the basics of calculation. So go through that one and make some problems which can clarify your all this basic calculation. Okay. Okay, we will start from gases. Gases. Here one ideal gas law. Ideal gas law. Ideal gas law. In ideal gas law, Boyle's law play very good mathematical example, which states that Boyle's law states that for a given mass of an ideal gas, the product of pressure and volume is constant at constant temperature. This means mathematically P into V equal to constant. Okay, here and as in Charles law states that for a given mass of an ideal gas, the ratio of the volume to temperature is always constant at a given pressure or constant pressure. This means V by T is equal to constant, or from Boyle's law we can say that pressure is inversely proportional to V. Means when volume increases, means when pressure increases means volume decreases. So when volume increases, then pressure decreases, and when volume increases, means when we increase temperature, then volume also increase. So volume is directly proportional to temperature, and this is Charles law. And pressure is inversely proportional to volume is Boyle's law. So combining both equation, we get ideal gas law, that is nothing but PV equal to PV proportional to RT, and for n kilomole of gas, this law becomes PV equal to nRT. Okay, and here R is constant, universal gas constant, and SI value is 8.314. If SI volume is given, SI unit is given, then we use this one. Otherwise we have to learn or calculate R value according to the problem. So in our Hagen and Watson textbook, all the units are given in British unit, so we have to calculate in SI unit. So here for gaseous mixture, in gaseous mixture, two or three gases are mixed. So partial pressure of the pure component or volume of the pure component taking places. So in Dalton's law states that total pressure exerted by a gaseous mixture is equal to the sum of the partial pressure of the component gases present in the gas mixture, Total pressure, how we can calculate the total pressure? So partial pressure of the individual individual gases which are present in the gaseous mixture, all the partial pressure, if we add the partial pressure of the individual component gases, then we find out the total pressure of the mixture. And same like Amagat's law states that the total volume occupied by a gases mixture is equal to the sum of the pure component volume. Simple mathematical is total volume of gaseous mixture is equal to the partial pressure of component volume sum of this one B, C and all this component volume, this one. Okay, now relationship between partial pressure, mole fraction and component of total pressure, fraction of component and total pressure. Relationship between partial pressure, mole fraction of component to total pressure. Okay, so partial pressure of component A is equal to the product of mole fraction of A into total pressure of mixture. So this one is partial pressure of component A and this is mole fraction of component A and this is total pressure of the mixture, and from here we get pressure percent is equal to mole percent. If anything is given, either mole percent or pressure percent, both are similar. Also volume percent is equal to mole percent, anything. So this implies that either partial percent is given, volume percent is given or mole percent is given, everything is equal and we can interchange anything. You can also verify this one. Okay, and average molecular weight of gases mixture. M average. M average is sum of molecular weight into mole fraction of ith component. Okay, i's come from 1 to n. So this one, so mi is molecular weight of ith component, and xi is mole fraction of ith component. Okay, so density of gaseous mixture, density of gaseous mixture. How we can calculate density of average mixture? So from ideal gas law, PV and RT, we get P average molecular weight by RT. From above we can get M average and specific gravity of gas equal to density of gas by density of air at same temperature and pressure. Okay, or molecular weight we can also calculate from the molecular weight of gas, that gas by molecular weight of air, that is specific gravity of that gas, gravity of that gas. Now if gas liquid mixture is given, gas liquid system, for gas liquid system two laws are coming. One is Raoult's law. Raoult's law state that at a given temperature the partial pressure of component A of a solution in the vapor is equal to the product of mole fraction of component A in solution in liquid phase and the vapor pressure of the pure component A. We write this one. States that at a given temperature the partial pressure of a component A of a solution in the vapor is equal to the product of the mole fraction of component A in the solution liquid, which is in liquid phase, and the vapor pressure of the pure component A. This is somewhat cumbersome, so simply we derive mathematical and we use in the problem, direct we use in the problem, but sometimes statement we have to write also. That's why you can go through this one. So PA, partial pressure of A in vapor phase. Okay, vapor phase. Partial pressure of component A in vapor phase is equal to pure component into mole fraction. This one is vapor pressure of pure liquid A. Okay, liquid. This one is in liquid phase. Mole fraction of A in liquid phase. For volatile component, in vapor, if volatile component is present in vapor, then YA is equal to PA by total pressure, this one, and from above PA is equal to pure component into mole fraction divided by total pressure. Okay, so here mole fraction of A, that is volatile component, that is volatile component in vapor phase, and here in liquid phase. So next comes to Henry law. States that the mole fraction of a solute gas dissolved in a liquid is directly proportional to the equilibrium equilibrium partial pressure of solute gas above the liquid surface. Partial pressure, this is mole fraction of A is directly proportional to the partial pressure of A. This comes to partial pressure of A is equal to mole fraction of A into Henry constant. This is Henry constant. Henry constant of component A. And Rawls law, the basic difference of Rawls law and Henry law is Rawls law valid for mole fraction of A close to when it's close to 1, and Henry law valid for x mole fraction of A close to 0. Then we use this formula. Now directly we go to simple problem. So first problem, calculate the volume occupied by 20 kg of chlorine gas at a pressure of 100 kilopascal and 298 Kelvin temperature. Solution basis 20 kg of chlorine gas. From here, moles of chlorine gas equal to mole. How we can calculate moles? Weight per molecular weight. Okay, so weight given is 20 kg and molecular weight of chlorine is 71, so it comes 0.2817 kilo mole. And ideal gas equation PV equal to nRT. From here V is equal to nRT by P. So everything we know, N equal to 0.2817 here kilomole. So R is 8.314 and temperature is this one 298. Okay, and pressure given is 100 kilopascal, so 100. So we calculate this one and it comes 6.98 meter cube. So volume is this one. Next problem. Calculate the weight of 1 meter cube of chlorine gas. Same, calculate the weight. Now we have to calculate the weight, so we need density at a temperature of 298 Kelvin and a pressure of 101.325. This is 1 atmospheric pressure, 1 atmospheric. Okay, solution basis. One meter cube of chlorine gas, So ideal gas law, PV equal to nRT. Here nRT, so N equal to PV by RT. Okay, so number of moles, N equal to P given is 101.325 into volume is 1 and R is 8.314 into temperature is 298. So number of moles comes is 0.0409 kilomole. Okay, kilomole. So weight of chlorine gas, weight equal to what? Weight equal to mole into molecular weight equal to 0.0409 into molecular weight of this one is 71. So here 2.094 kg. And next problem. Natural gas has the following composition by volume CH4 equal to 82%, C2H6 equal to 12%, and N2 is equal to 6%. Okay, calculate the density of gas at 288 Kelvin and 101.32 kilopascal, and composition in weight percent. Okay, solution: basis 100 kilomole of gas, 100 kilomole of gas. So now basis is 100 kilomole, that's why when it's in percentage, so we can take as a kilomole of CH4 equal to 84. Okay, directly kilomole of C2H6 is equal to 12 and kilomole of N2 equal to 6. Now mole fraction that is mole fraction of CH4 is equal to mole fraction of CH4, that is total mole is 100, so 82 by 100 equal to 0.8. Likewise mole fraction of C2H6 equal to 12 by 100 equal to 0.12, and mole fraction of nitrogen, mole fraction of nitrogen equal to 6 by 100 equal to 0.06. So, and molecular weight of CH4 equal to 16, and molecular weight of C2H6 equal to 30, and molecular weight of N2 equal to 28. So M average molecular average molecular weight equal to mole fraction, that is M into fraction of A. Okay, so molecular weight of CH4 is 16 into molecular weight, this one is 0.8 and 0.82 plus 16, here is 30 C2H6 is 0.12 mole fraction plus 28 into 0.06. So M average comes as 18.4. Therefore density of gas equal to P M average by RT. P given is 101.3 into M average is 18.4 and R is 8.314 into T is 288. So density of gas is 0.78 kg per meter cube. per meter cube. So in kg, CH4 in gas mixture equal to 82 mole fraction into molecular weight of CH4 is 16. This comes 1312 kg. And C2H6 in gas equal to 12 into molecular weight is 30 equal to 360 kg. And N2 in gas equal to 6 into molecular weight 28 equal to 168 kg. So weight percent CH4 equal to kg of CH4 divided by kg, यानी total kg of gas into 100. So individual we can calculate component quantity in kg, quantity in kg, and weight percent. So CH4, C2H6 and N2, this is 1312 and this is 360 and 168. Total is 1840. So weight percent is kg of CH4. This is 1312 divided by 1840 into 100% equal to, this comes 7.371. .3%, and this is 19% and this is 9.13%. Total is 100%. Okay. You go through the book and do as much as possible which is given in the book, unsolved problem. So you will get thorough knowledge. Closed vessel contains a mixture of 40% NO2 and 60% N2O4 at temperature 311 Kelvin and pressure 531.96 kilopascal. When the temperature increased to 333 Kelvin, sum of N2O4 dissociates to NO2 and pressure rises to 679.95 Kelvin. P1 and P2 is given. Calculate the composition of gases at 60 degree centigrade by weight. Okay, solution. Basis 100 kg of gas mixture. NO2 in gas mixture equal to 40 kg and N2O4 is equal to 60 kg. So moles of NO2 is equal to 40 by 46. Weight by molecular weight is 0.87 kilomole, and moles of N2O4 equal to 60 by 90. Molecular weight of N2O4 is 92. So 0.652 kilomole. So initial mole is equal to 0.87 plus 0.652 equal to 1.522 kilomole. And reaction is N2O4 dissociates to 2NO2. Let X be the kilomole of N2O4 dissociates at 333 Kelvin, and NO2 formed is 2 mole, so 2x kilomole. Therefore N2O4 at 333 Kelvin equal to 652 minus x kilomole, and NO2 at this temperature equal to 0.87 plus x kilomole. This is 2x. Therefore total moles at 333 Kelvin equal to 0.652 minus x plus 0.87 plus 2x. This is 1.522 plus x kilomole, and P1 V1 equal to P2 V2. For closed vessel, V1 equal to V2. So P1 by P2 equal to N1 by N2 into T1 by T2. So from here P1 531.96 divided by 671.79.95 equal to 1.522 divided by 1.522 plus x into 311 divided by 333. If you cannot understand that one, then you again go through the problem and see from where this calculation comes. So from here 333, x comes as 0.295 kilomole. Now NO2 at 333 Kelvin equal to 0.87 plus 2x equal to 0.87 plus 2 into 0.295 equal to 1.46 kilomole, and N2O4 at 303 Kelvin equal to 0.652 minus x equal to 0.652 minus 0.295 equal to 0.357 kilomole. Amount of NO2 at 333 Kelvin equal to mole into molecular weight 46 to 67.16 kg, and N2O4 at this one equal to mole into molecular weight equal to 32.84 kg. So composition of gases at 333 Kelvin, that is component, two component is there, NO2 and N2O4. Quantity in kg, here total quantity in kg of NO2 is 67.16 and here 32.84. it comes 100 kg and weight percent is 67.16 and 32. We have taken more basis 100 now, that's why its weight percent is this one. So completed. Thank you, student. You go through this one and very good afternoon.